So in video 11, we're getting into molecular orbital theory, which kind of fills in some of the gaps for Lewis, Vesper, and valence bond theory. And some of molecular orbital theory, or actually most of it, is beyond what they would say the scope of AP chemistry is. But we also need to remember that AP chemistry is giving you the opportunity to test out a first year chemistry in college, depending how you do. And if you jump right into second year and you haven't heard about molecular orbital theory, then you're going to be very far behind in terms of understanding resonance, in terms of understanding some of the other properties of covalent compounds that Lewis theory, Vesper theory, and valence bond theory cannot describe. It's referenced in the AP curriculum, but most of the references don't require you to know much about molecular orbital theory. So don't stress about this. Just listen to it once through really quick and know that it helps us to kind of fill in the things we can't understand or to prove and support the things we do understand. So a molecular orbital is an allowed energy state for an electron in a molecule, very similar to an atomic orbital. It's a wave function, it's a mathematical equation, and it's telling us the most probable location. And it takes our atomic orbitals and turns them into something new. So just like with hybrid orbitals, we can take two orbitals and make two other orbitals. But if we have two atomic orbitals, we will make two molecular orbitals. But this isn't talking about two atomic orbitals or three atomic orbitals or four atomic orbitals from one atom. This is talking about when the atomic orbital from hydrogen and from another hydrogen combine, what sort of orbitals do they make? They still hold two electrons, just like atomic orbitals do, but they only hold them when they're spinning in opposite directions. So a lot of the rules, even the Aufbau principle, Pauli exclusion principle, Hund's rule, are still going to apply here. The new idea is that when we combine these orbitals, there's places where we can put electrons where they are bonding, but there's also something new called an antibonding orbital. So a bonding orbital is where those atomic orbitals are combined to form a place where the electron density is a maximum in the internuclear region. It is from constructive interference or constructive combination of these. So we're getting back to that idea of a wave function. And waves can interfere with one another constructively or destructively. And when they interfere destructively, we have an antibonding orbital. We have a place between the two nuclei where the electrons cannot be found. We have a node, a minimum electron density between the nucleus. So as we think about this, that means that we know where some of the electrons are when they're in a bonding orbital, but the antibonding orbital means we know that they are not there. And we still use that sigma and pi notation that was used, but this time it's connecting a little bit more directly with the s orbitals and with the p orbitals. And maybe you didn't really see the connection before, there wasn't a big mention of it, but pi bonding always occurs when p orbitals overlap side by side. So p orbitals can overlap end to end and be a sigma bond, but when they're overlapping side by side, it's a pi bond. But here, we're going to end up using the sigma and pi to represent the s and the p orbitals. So molecular orbitals that happen along that internuclear axis are sigma bonds, same idea as before, but if they are overlapping outside that axis, they're pi bonding. Same thing we had before. But with antibonding, it's shown as an asterisk, but it's read as star. So it's sigma star and pi star. And right here we have the electron configuration of hydrogen. And there's just a couple features of this that I want to highlight as we go on. One thing that's important is we have our 1s, we have our 1s, so that's going to combine and make two orbitals. It's going to make a sigma bonding orbital and a sigma star antibonding orbital. So we've combined two atomic orbitals and made two molecular orbitals. The bonding orbitals are always, and it says it up here, lower in energy than the atomic orbitals from which it forms. So this is where the idea of the additional stability comes from. This arrangement of electrons is more stable than the electron being there and being there. And as we start to look at other bonding combinations, we can understand what's happening or why things bond and why things don't by looking at that relative stability. So the next one we have here is helium. So helium we think of as not being able to bond. Molecular orbital theory explains why it can't bond. The 1s orbital and the 1s orbital are both full, so if we combine those, we make a sigma 1s and a sigma star 1s. And when we put the electrons in those, this fills, so we have a bonding orbital. That's actually more stable than when the electrons were just in the helium atoms by themselves. But this one is less stable. So as a result, He2 is less stable than having two separate helium atoms. So those two separate helium atoms being more stable means that it's not going to form this bond. Or, as it says, it's unlikely to form. And the great thing about this theory, or about molecular orbital theory, is that it helps us to know certain things. Helps us to know about bond energy, bond length, bond order, and down here, magnetism. So bond order. This may be the most important thing to pick up out of this video is the number of bonding pairs between two atoms minus the antibonding pairs, or what it really is. A bond order of 1 is a single bond, a bond order of 2 is a double, a bond order of 3 is a triple. So those of you who are watching this video, even though I said it wasn't going to be tested all that much, are going to be more prepared for the test, because you're going to know that triple bond means a bond order of 3. Or if we have resonance with a double bond on one side and a single bond on the other, that would be a fractional bond order, a 1.5, which supports the idea of resonance. The higher our bond order, the higher the bond energy. So this gives more proof of that high bond energy, or more prediction of it. Even if it's a molecule we can't form or is unlikely to form, we can predict what the bond energy will be. And the bond order will be inversely proportional to the length, because high energy happens when we have a short distance. Longer bonds are lower bond energy. So we're still following the same atomic orbital rules, as I said before, filling from the bottom to the top, spreading out, can't double up. But every now and then we get into a weird pattern. And that happens with boron, carbon, and nitrogen. And when I say a weird pattern, you know how the 4s fills before the 3d? That's the same idea here, where sometimes the pi fills before the sigma. And you're not going to need to memorize this. You don't need to know all the different things that happen. But it's just important in terms of understanding these things. So we have boron, carbon, nitrogen, oxygen, fluorine, neon here. The molecular orbital diagrams for each one, and we see a certain property. We can see the bond order for each. So when boron forms, it's a bond order of 1. If C2 forms, it'd be a double bond. It'd be a bond order of 2. But once we start to get into the molecules that actually do form, so we should be able to recognize these are compounds that actually form. These are gases, diatomic gases. N2 is triple bonded. O2 is double bonded. F2 is single bonded. So it describes that, and we can also think about the bond energy. The triple bond has the highest energy, double bonds next, single bonds less, and the bond length, if I clean that up a bit, get rid of those, there we go. We see that the triple bond is the shortest, double bond is next, while the single bond is the longest. And as we get to neon, and we could do the same thing with helium, the bond order is 0, meaning it's less stable when bonded than it is when it's separate. And we could go down to argon and say the same thing. But then once you start to get to the noble gases below that, you can see they actually could form, but they're still going to have that bond order of 0. The last thing that it has is magnetism. Paramagnetic and diamagnetic are important terms to remember, and with diamagnetic, remember that means the magnetism dies. They are not magnetic at all because all of the electrons are paired up. Even this one would be diamagnetic if it could exist. But when B2 forms, if it forms, it would be paramagnetic. But more importantly, oxygen, which actually forms, that gas is magnetic. When you put it in a magnetic field, it is attracted to that magnetic field because we have some unpaired electrons spinning the same direction. So you're looking for paired and unpaired electrons. The paired electrons cancel each other out. The unpaired electrons do not. And then when we get, and you can just read through this quickly, if we get two elements that aren't the same, nitrogen and oxygen, for example, we can describe NO a little bit better. And that's what this picture does. NO is one of those weird examples where we have an odd number of electrons, and this helps us to understand what's happening with those odd number of electrons. But there's differences in stabilities related to electronegativity. This describes all of it, and you won't need to know it in that much detail, but do know that there is an explanation there. This gives you a very basic look at it. Your textbook gives you a little bit more. And then when you go on into organic compounds, when you go on into second year chemistry in college, you're definitely going to spend more time with this. If we have a large molecule, just like we a lot of times with those larger molecules kind of split apart the Vesper diagram into pieces, we do the same thing. Well, not the same thing, but we kind of simplify or only look at certain parts of the molecular orbital diagram also. So that's bonding. Obviously, the bulk of the videos are over covalent. Covalent has so many more topics, but it's very, very important that you understand the ideas of ionic, that you can connect Coulomb's law to things like metallic. There's lots of diagrams in this. Make sure you're ready to interpret a graph and know what that means. Make sure that when you see a molecule that you draw the Lewis structure. Those are all key things. When we get to intermolecular forces and states, we'll come back to some of these bonding things, come back to polarity, come back to metallic, come back to ionic. So do not forget these big ideas, because actually on recent AP exams, there's been a lot more IMF questions than bonding questions, but understanding IMFs is based upon understanding bonding.